Okay, here shows how the filter are designed. The filter can be expressed by this system function like this one. The inverse Laplace transform is ht. Input in the time domain is xt. In the Laplace domain, it can express the hxs. It's the same. Output yt is time domain expression, and in the spectral the s domain it's ys. The system function hs transfer function is a ratio between ys over xs. So this one is input and output. The ratio gives the transfer functions. In the time domain, here is a typo t to the n. Okay, the time domain expression for yt and xt are given as a differential equations. The an, a1, a0, okay, here is y should be added. So an, a1, a0 are coefficient of the y, and bn, b1, b0 are coefficient for the x. Okay, by taking the Laplace transform, this equation can be converted a, and the differentiation can be replaced by s. The nth order differentiation is an times sn, and all the way down an minus 0 and a1. That's the one derivative, that is s, and a0, and factored out ys. This is ys in the Laplace domain. And similarly, right hand side also converted the Laplace transform, then it will give bn sn, s over n, and bn minus 1 will give s n minus 1 like that, and it will give up to b0. Okay, and factor the xs. Then by taking the ratio ys over xs will give this expression. So this one is a transfer function for this system. So many system can be expressed by difference or differential equations that can be converted into transfer function like that. So at this moment, I hope that you get some idea what's the meaning of HS. Okay, differential equation in between the input and output can be converted in the Laplace domain, then that will give the transfer function like that. So we would like to implement this one. To implement this one, we need to design some architecture. How are we going to implement that one? So we can decompose this one into a little bit different forms. I mean that HS is actually y over x. So this one is basically y over x. Okay, and this can be modified in this way: y1 over x times y over y1. I would like to modify this one in such a way, then y1 will cancel out, then it will give the same result. That is defined over here. y1 over x is defined in these equations. What does this mean? We know that the y y1 over x has only poles 1 over all the other things, like this way. Okay, and all zeros are numerator of this one. That is defined over y over y1. Okay, so we decompose the numerator and denominator in two different steps. If we defined h1 is y1 over x, h2 is y over y1, then h will be h1 dot product h2. h1 h2 product will give this result. Okay, this is defined h1 and this one is h2. Then by use of these equations, we can convert as nth order y1. Okay, just multiply this one, that will give this result. You can see here that if you multiply this one, an s to the n plus and everything included here, and a1s and a0 and y are equals to x. Okay, then I would like to express Sn to the y. Sn to the y, then 1 over an is divided here, then all the other component will be moved to the left right side, then it will give these expressions, and divide by 1 over an. Then we can define Sny1. That is given in these equations. We need to implement this one by use of this architecture. So at here, this nibble means subtraction between input and output. So we subtracted, adding the x and subtract all the values of this one. So 1 over an is this part. Okay, that's this one. So we need to evaluate all the inside of this one. We need to adding like that by factoring that one. That is calculated over here. We know that the 1 over an should be s to the n times y1. That's this one. And we use 1 over s. This one is integrator operator. By s is differentiator, d of dt. But 1 over s, we can implement that one by use of integrator. By use of integrator, we can create this one. So the integration circuit is added here. Then that will give s n minus 1 y1. So that is multiplied a n minus l. That's this one. And also all the way the same. And then lastly, a0 y1 is added here. And then summing up, and finally we subtract. In these notations, all this dot is adding, but this one is subtracting. And scaled 1 over an, that will give this equation. So this equation is implemented by use of this architecture. So each point of this one, it means that these values, and at the bottom it is y1. Okay, and to apply h2, we need to using these equations. It means y are given in this way, so we can calculate this part. We know that the Sn to the y1 is this node. This node is scaled by Bn. Okay, and added. So this is a sum, but this one is a subtraction. So all the other nodes are summing up. And the next one, Pn minus 1, Sn minus 1, S to the n minus 1 y1 is this node. That's this one. Okay, this node is this one. And multiply the Pn minus 1 and add it. And similarly, weighted sum of all these values will provide y. So the filter can be implemented by this kind of structure. So we call that is canonical forms. Okay, we have the previous example like this one. So how are we gonna express that one? So that is hs r 9 over s square plus 10s plus 9. We would like to draw this one into this canonical form. Then firstly we need to understand this part first. So x is input is provided, and that should be subtracted, and an is 1 at this moment. Okay, this one is s to the 2 y1. So that's this part. At this moment n is 2, and this one is integrated 1 over s. So this one is integration operator, and this one will be sy1, and this should be multiplied by 10 and add, and we have another integrator, and this becomes the y1. y1 is multiplied by 9 and subtracted like that. Then to get the y, we need 9 point of that one. 9 of this one becomes the y. So this is the architecture for these systems. We have 2 integrator, and we need some weighting factor like that. So this is the final weighting factor is coming out from this node. There is no s, so it can be expressed in this way. But in general, second order system, general second order system can be expressed in the similarly. It's b2 s square and b1s plus b0, and a2s plus a1s a0. Okay, so this should be second order. Okay, like that. The second order lattice structures can be drawn on here like this way. Okay, this one is a subtraction. Except this node, every node is adding except this node. So it specified like that symbols. At this moment, we are using the 1 over a2. Okay, so this node will become s to the n. At this moment, the second order, s to the s square and y1. And by taking integration, it will become s y1 node, and we multiplied at this moment a1. This is weighting factor for sy1 node, and last node we have another integration, then this becomes the y1 node, and the weighting factor is a0. Okay, then to find out the output expression for y, we need to include this part. So weighting factor for s square is b2, so we have to multiply the b2 and this node, and for s times y1 we have to weighting factor is b1, and the last one is weighting factor is b0, and weighted sum, all of this sum will give y. So this is called the second order lattice. When you see the maybe okay. The transfer function related packages are included in this signal, so you can search some functions of signal, then you can list up all the functions. At here you can see transfer function to SOS. That is a second order system transfer functions. How we gonna converting to this one? That is the signal tf2 as second order system. So this one will converting any given function with second order lattice structure. Okay, that is a second order lattice structure. This one, and in general, this one is a canonical form for any given filter.